Hello everyone. Welcome to our lecture number 15. I hope that you're all doing well. In this lecture I'm going to talk about the topic of entropy balance in reversible and irreversible processes, and we're going to solve the second example, which is posted online, and it has two sections. In the first one we're going to solve for the mass flow rate which passes through the system, the turbine. And so therefore we need to implement the first law for flowing fluids, flowing like in open systems. And in the second section it asks for isentropic efficiency. So we need to find the entropies or enthalpies at two different states of this process. So for the first section, I'll directly solve it. But in the second one, I'm gonna, sorry about this. So I'm gonna, here's my notebook, okay? But in the second one, I'm gonna talk about a little bit of concepts and equations about isentropic efficiency in turbines and compressors. Then I'll solve for whatever is asked, I guess, which is the isentropic, um, which is in the second one, the part B, yes, isentropic efficiency of the turbine. Okay, great. So let me read the whole example for you just to imagine the whole story. Then we're gonna go through our steps, which are defining the system, clearly asking the question, and make some assumptions, simplify um, the knowns, the parameters that are known or given by the text, by the question, and write our summary table. Then implement the first law and solve for enthalpies, entropies, and so on and so forth. So let me read the question for you. It says steam enters an adiabatic turbine at 5 megapascal. Wow, great! It's a compressed steam, and the temperature is 650 degrees C. Oh my god! And the speed, the inlet speed, is 80 meters per second, and then the steam leaves at 50 kPa, so the pressure drops drastically, and the temperature as well. So the second it says leaves at 50 kPa and 150 degrees C, and speed is 140 meters per second. So as we see in turbine, as the gas passes through different stages of the turbine, it accelerates and the speed and it speeds up. And on the other side, pressure drops and temperature drops, which makes sense, right? Because pressure, like being compressed and hot, means that the steam has the potential to do work, and it does work. So it gives us this work as the output, and also the potential energy will be converted to kinetic energy, in which we in the question we observe that the velocity speeds up. Then it says if the power output of the turbine is 8 megawatt, so that we have only W dot out, right? It's a power and it's just outlet. Like in compressors, we give the work, we do the work on the compressor. So we help the compressor to compress something, right? But in turbine, it's the other way. We give the potential energy to the turbine, and turbine gives us work, right? Then it says determine A, the mass flow rate of the steam flowing through the turbine, and B, the isentropic efficiency of the turbine. Great. So here's our example number 2. The first step is to specify our system. And as it's obvious in the text, It's all talking about a turbine, just one turbine with an inlet and outlet, and apparently this turbine gives us work. So all I need to do is just to pick the content of this turbine, and so the system is turbine content, which is some sort of like steam. And since we have inlet and outlet for both energy and mass, therefore the system would be open. It's mentioned that the turbine is adiabatic, right? Which means there is no flow of heat flow, or heat flux. It's better to say heat flux, in or out. It is totally isolated. So heat is not, energy is not allowed to escape or enter the system through a temperature difference. Like the casting, or like the walls of the turbine is totally isolated with like isolator. And also, the question is talking about is constant velocity or constant properties at the inlet and outlet, which means that we're dealing with a steady state operation, right? The turbine is working, so, and it's gonna work forever. Like right now, there are many power plants that has different units, and each unit has a turbine, like gas turbine, and now they're running, and the condition wouldn't change tomorrow or the day after, and they were like same as what they were like yesterday. I mean, it's steady state in time, right? In sorry, in time, the operation is steady state, which means that there is no change in time in rate of energy. And the question is mentioning something about like inlet and outlet velocities. So it's telling us that, oh, separate. Please pay attention that you're gonna include the kinetic energy in your equation. So far we've been just like canceling out all those v squares divided by 2, but now here we are not able to do that. We are not allowed to do that. So velocity is mentioned, therefore kinetic energy is not zero. Although there's nothing mentioned about like different heights or like gravity and stuff, so the potential in energy is still zero, is still negligible. um the PE or like the GZ part in our equations, they're all zero at both points. And let me draw the system. So here is my turbine real walls, and here is the inlet and outlet. But there's a question: which one is, these dashed lines are inlet and outlet, or imaginary boundaries? But the question, I have a question: that which one is what? Which one is inlet? Which one is outlet? We have these schematic pictures of turbine and compressor, right? And as we know, as I told you before, in the turbine, the gas kind of like expands, the pressure drops, and it accelerates. So it's when the pressure drops, it means like it's kind of expanding, right? So the mass, the flow should be like coming from here and then expands, it diverges, and then leaves. But in compressor, it's the other way. So here is compressor, right? You compress it, you just like kind of like squeeze everything, and then shoots it out, right? So here's the difference between turbine and compressor schematic pictures. And let me define point 1 and point 2 as inlet and outlet corresponding. Yes, in order, point 1 and point 2 inlet and outlet respectively. So here is m dot in and m dot out, and here is no leakage or any external or like separate outlet, so mass is conserved. So m dot in should equal m dot out, and I'm gonna mention that in future. And also that would be like E dot in carried by the mass going into the system, and E dot out leaving the system as well carried by mass, because I am drawing these arrows across this imaginary boundary, which means this energy rate is related to mass flow. So it has to be carried by mass. If you're talking about something which is not carried by mass, so that energy rate should be crossed through real boundaries, which would be work in this case, right? So the turbine is giving us W dot out. It's providing the work. That's it. So what is the question? The question is how much is the value for the mass flow rate? Here's the question. So as always, I need to write my summary table. And this week I'm gonna post some lectures about cycles. And in cycles, you're gonna have different parts like turbine, compressor, a combination of all these guys. And at that point, you're gonna have like 8 points or 6 points. Let's say you have three devices like a compressor, turbine, and like a valve. Then each of these devices has two, like one inlet and one outlet. So if you define 2 points for each, then there are three devices in total, so you're gonna have 6 points in total. So you have to write this what is it called, table. It's all my experiences. I'm just sharing my experience with you. P1 is, what is P1? Question. Okay, 5 megapascal, and it says that T1 is pretty high, 650. So without even checking the tables, I can tell this is superheated vapor, right? Because it should be crazy. That steam should be super powerful to do work, right? Like ready and like, yeah. So, and then the velocity V1 is, how much is it? 80 meter per second, and then it leaves at 50 kPa, and the temperature is 150 degrees C, and the velocity outlet is 140 meters per second. That's all we know, plus so plus W dot out is given 8 megawatt. Yes. Okay, so at this point I need to um, implement the first law. Why? Because I'm gonna solve for the mass flow rate, and I know that the only place that I have this mass flow rate included is the first law. And so let me tell you, if you check lecture note number 9, pages 12, 13, 14 once again, then you're gonna see what is the formulation of the first law. And I'm gonna write it again for you. It is Q dot plus W dot plus the summation over all these energies, E dot in and E dot out, these two guys, the summation over all the inlets and all the outlets. So that's going to be sum over m dot h plus V squared divided by 2 plus GZ. The whole guys are at the inlet, and that's gonna equal to Q dot plus W dot plus the summation over M dot times all these energies. And you might ask, Sepper, why are you using the enthalpy version? That's a great question if you ask, and I'm sure you're asking now, it's in your head. And let me tell you why. Because here we're dealing with a flow, and a flow has flow work. And we know that H enthalpy equals U, which is internal energy, plus PV, which is the flow work. Therefore, by using H, by including H in our formulation, we are indirectly include the effect of flow work, right? That's why I'm not using U. I'm not using the other version. Um, so, and I skipped the fact that the first law says E dot in minus E dot out equals D, like E dot over dt, because it's steady, so the right hand side is 0. Then E dot in equals E dot out, and I just directly wrote here, this is E dot in, and this is E dot out. But these parameters are different than those, because here I'm including the W dot as well. So don't mix them, don't confuse between these guys. I mean, the E dot here is like all different types of energy transfers, like heat, work, and carried by mass, and heat, work, and carried by mass. And then as I assumed, like here I have some assumptions, right? I know potential energy does not change, and it's adiabatic, so the heat fluxes are gone. And it's a turbine, and it gives work, it provides work, so I'm just gonna have W dot out, so this guy goes home. And so at the end, I'm gonna have M dot, and let me write it here. Yeah, so let's say M dot 1 times, well, H or in, let's say in, okay, here I'm here, H1 plus V1 squared divided by 2 equals W dot out there plus just the H is remained, so M dot out, here's the subscription, times H2 plus V2 squared divided by 2, right? And if I rearrange all these guys and keep W dot out on the right side and just take the rest of it to the left side and factor M dot, because let me write it here, that mass is conserved and we have only one inlet and one outlet. Therefore, instead of M dot in and M dot out, I'm gonna make the life easier for myself, so I'm gonna just use M dot, which I mean M dot out and M dot in, they're equal. Well, so that's gonna be this guy, H1 minus H2 plus okay, V1 square minus V2 square divided by 2. That's it, right? And awesome, we have this table right here, right exactly where I want it to be. So listen, check this out. I'm looking for this guy, right? And the W dot out is there. Awesome. Left side is given. Then the V's, the velocities are given as well, V1 and V2. All I need to do is just to solve for H1 and H2. If I get these two guys, then I can put in everything there and just solve for M dot, right? It's easy. That's why I told you that I'm gonna, oh my god, sorry. That's why I told you I'm gonna use the first law, because the first law is the only thing that includes the mass flow rate. So, which means that, okay, so at this point I need to pause and I need to go through my summary table at each point, go to the property tables and so and find enthalpies. So at point 1, what do I know? I know, please, 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 that the material is R1. No, 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 it's not. It's steam, it's water, right? H2O. Steam. Okay. And if I go to this table, so at what's the pressure? The pressure is 5 megapascal. Okay. Ding. A5. There you go. 5 megapascal. Well, that's enough. So the temperature, the saturated temperature, which would be the temperature in the phase change process, is 263. But the gas steam at the inlet is at 650 degrees C, which clearly says that it's superheated because the temperature is much larger, it's much warmer than saturated temperature. So on the graph, we have passed the saturated line and we went up, we've gone up to higher pressures and higher temperatures. So I need to go to the tables about superheated steam at the pressure which is 5 megapascal and the pressure and the temperature is 650. In this table, I have all the properties, useful properties at two different pressure temperatures, 600 and 700. 600 and 700. But the question is talking about 650. It's kind of like an uh, interpolation, but interpolation, and but it's just averaging because the temperature is right between 600 and 700, right? So let me show you. Okay, I'm looking for H at right in between this value and this value. So just take the average of these two guys. That H would be at the average of these two temperatures, which is 650, and is exactly what I'm looking for. And I'm gonna do the same thing later on for entropy in between these two guys. Just want to tell you in advance. Well, so let me write my judgment once again. So the saturated temperature at this pressure was 263.94 degrees C, which is much less than T1, which is 650 degrees C, and therefore we conclude that the steam is superheated. Then we checked table A6, which is for superheated properties, and we found H1 at 5 megapascal and 650 degrees C, which was the average of 66.9 plus 39.3 3783.6 kilojoule per kilogram. And I'm gonna do the same thing again, same procedure at point 2. The material is steam, and all I know is temperature and pressure. So two intensive properties which are enough to specify the status of the matter, the material, right? So once again, let's go to this table, but at a different pressure, which is 50 kPa. Where is it? 50 kPa. So let me scroll up a bit. 50, 50. Where are you? Okay. And the saturated temperature is 81, but there it's the temperature is 150. So again, it means that our hero, which has done work, the steam, and like gave us what? Gave us 8 megawatt. Is superheated. I'm just trying uh, to prevent you getting bored. So 50 kPa, that is 81.32 degrees C, which is less than the given temperature. So steam is superheated. And I need to go to the other table and get H2 at 50 kPa and 150 degrees C, which is 2780.2 kilojoule per kilogram. So let me show this equation again. So now, boop, oh, doop, doop, we got them. So all I need to do right now is just put in everything. And please be careful that the units are important. So keep them in your formulation because you're gonna play with them. I'll show you here. So here I'm talking about kilojoule per kilogram, right? For both. Plus the difference between velocity squares, v1 and v2 divided by 2. And I know that the unit it would be meters square per second square, right? So I know that the mass flow rate here would be like in kilogram per second, right? How much of mass in time. So like let's assume this guy is gonna be like kilogram per second. Therefore, kilogram would cancel out with kilogram, and I'm gonna end up. I mean, just let's talk about just here. Okay, the first part. Then the product of this term by this term would have a unit of kilojoule per second, which is kilowatt. And comparing to the other side, they match. But on this side, I have meters squared divided by second square. Where is kilojoule? Where is second? Sorry. Where is kilojoule? Where is kilogram? Right? So I need to convert that unit this way, saying I know that 1000 meter square divided by second square is 1 kilojoule per kilogram. You can do it by yourself. You can check it. It's easy. Just kilojoule is like energy. Energy is force times displacement. It's meter, and the force is Newton, which is like m times acceleration. Then like if you go like down in fundamentals, like the basic of the units, then you can cancel out everything and end up with this unit. I mean conversion. Now everything matches. Kilojoule per kilogram. Doop doop. So doop doop dun dun. Right? Kilojoule per kilogram. Kilojoule per kilogram. Therefore, all is fine. That m dot is 8.029 kilogram per second. Awesome. So thank you for listening so far. Now I'm gonna switch. I'm gonna solve for next part B, which asks for the isentropic efficiency of the turbine. So I need to rewrite. Oh my god. Why? Okay. So I need to rewrite the question that I'm gonna answer. So the let's say like the isentropic efficiency of T, which represents turbine, how much is it? Please check this lecture, pages 4 and 5. Thank you. And as you see, it says that the Isentropic efficiency of turbine is defined as actual turbine work divided by isentropic turbine work, which in our case it's W dot out divided by W dot isentropic, which I'm gonna show you with like subscription of S. And also it says that isentropic efficiency for compressor C is, wow, it's reversed. It's isentropic compressor work divided by actual compressor work. So students have been asking me a lot of times, so many times, that why is it this way? And it's difficult to memorize, right? In exam you might get confused. Oh my god, which one was what? Like the turbine was actual over isentropic, or what was that? It's pain. I know it's pain. So I want to help. I want to tell you a trick to memorize these two um, equations easily. How? We are talking about efficiency, right? Efficiency of a turbine or efficiency of a compressor. And we know that when we want to talk about an efficiency, in our thoughts, like behind our thoughts, we assume an ideal world, right? An ideal nature. Everything is good, everything is perfect. There's no loss of energy. There is like the best, right? In that world, everything, all the processes would be isentropic, and entropy would be constant. In that imaginary, in our imagination, that imaginary world, entropy is constant. So please, all you need to keep in mind is that an ideal world, an ideal process would be an isentropic process, that we do not change the probability of making a chaos or changing the probability of chaos, having a chaos, which is represented by a parameter called entropy. So whenever the entropy is constant, it means the process is isentropic and we are in an ideal world, right? Good. Now let's talk about turbine first. How would a turbine behave? How would a turbine give us work if it was in an ideal world? If the isentropic, if it was operating in an isentropic process. In this case, entropy would be constant and turbine would be a better guy. Good boy, right? Good girl. So the turbine gives us more work, right? Because there's no loss, there's no chaos, there's no intermolecular fights between molecules, which makes a chaos, right? Entropy is constant, everything is perfect. So the turbine gives us more work. And we know that efficiency, that we define something as efficiency, should be less than 1, for sure, right? The best efficiency is 1, and in real world, in real process, efficiency is less than 1. So in the exam, or when you're solving a problem in thermodynamics or in any other majors, First, define your ideal world and then judge that the device, which might be turbine or compressor or anything else, how would that react? So for turbine, the isentropic work is more than actual work. So the turbine, if it works isentropically, it gives us more work. It's a better turbine, right? It's a better turbine. So when you make this portion, you're gonna put the more work, the greater work in the denominator, and the less work in the numerator. So that's why we say the actual work divided by isentropic work, because we're sure that in an ideal world, turbine gives us more work. So the isentropic turbine work is larger than actual turbine work. But in a compressor case, again, in an ideal world, compressor is a better compressor. So it stands on its own, right? It's like a strong person. And it says, whoa, 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 I don't need that much of work anymore. I can compress this gas for you with less work. Don't give me that much work. I'm not gonna have waste. I'm not gonna make a chaos. Just give me a little bit of work. I'm gonna compress it for you. No worries. See? This is an ideal compressor. That's why we define the isentropic efficiency for compressor as isentropic work divided by actual work, because we know that an isentropic work is less than actual work. It's a better compressor. It requires less work to give us the same pressure difference, right? It's a better compressor. It needs less work, and it does it with like needing or like with like need this need of less need of work. Okay, so that's why we define them like reversely for turbine and compressor, because one, the turbine gives us work, and in an ideal world the isentropic work would be higher, so it should be in denominator. But for compressor, we give work to the compressor. So in an ideal world, we give less work to get the same pressure difference, the same compression ratio. So that should be in the denominator. Thank you so much for listening. I'm gonna be quick because from now on it's gonna be much more easier. So I'm looking for this guy, and I know how much is the actual turbine work. It's given in the text. It's 8 megawatt. So all I need to do is just to find isentropic turbine work. I need to implement the first law again, but now at this time I know mass flow rate. So I'm gonna solve this equation one more time, but I have m dot and I have the velocities, and I'm looking for w dot out as if the process was isentropic. So H1 would be whatever it is, but H2 is gonna change, right? Because now you are changing the operation condition. You are assuming that it is isentropic. So H2 would be something else. So I need to assume, listen to me, I need to assume that the process was isentropic. Then it means that S1 equals S2, and I need to find the condition or the status of the outlet steam uh, based on the fact that as if the process was isentropic. So let me put a note for you that we should solve for the W dot out sub S, which means isentropic, as if which means that then S2S, which means like the entropy at point 2 as if it was isentropic, so sub S again, would equal S1. So now I need to again check the. Do you remember in the beginning when I was talking on the table, I said I'm gonna do the interpolation once again for another time for entropy? This is exactly right now because I don't know how much is S1. I don't know how much is the entropy at the point 1 at the inlet. So I need to go at point 1 again and just solve for entropy. Just look it up. And I'm not going to go through the process because I know already that it's superheated. I've done the comparison and stuff. So I know that the material is superheated steam, H2O, and therefore S1, so S1 would be the average, sorry, A6 is stable. So S1 at 5 megapascal and 650 degrees C would be the average of these two values. 7.5136 plus 7.2605, both at that unit kilojoule per kilogram point Kelvin. You can find a unit up there above the table, equals 7.3870 kilojoule per kilogram Kelvin. And now we have defined a new point 2, point 2s, which means, once again, as if the process was isentropic. So it means that we're going to have the same pressure ratio and P2 would be same. So let's say P2S. Everything now has a subscription of S. 50 kPa, and then S2S equals S1 that I've just got it a couple seconds ago. I'm doing all these to find the status, the condition of steam at the outlet, to find how much is enthalpy and just put it back in the first law and solve for W dot out. So now I have two intensive properties, pressure and entropy. And all I need to do is to find the entropy at saturated liquid and saturated vapor at this pressure, 50 kPa, and then compare those two values with this entropy that I have, and then conclude if it's subcooled mixture, liquid vapor mixture, or superheated mixture. Superheated um, vapor. So based on table A5, which is about the saturation properties, SF at 50 kPa, F means fluid, is 1.0912 kilojoule per then this number is in between these two guys. Which means we are right in the entropy value is right in between the entropy for saturated liquid and saturated vapor. So we have a mixture. We have a liquid, vapor, mixture. As soon as you understood, you realized that you have a mixture of liquid vapor, the next step would be like rapidly would be to find the quality of this mixture. How much of that is vapor and how much of mass, like based on the total mass, is liquid. So that would be like S, so, and all these calculations are based on the entropy. So S2S sub S minus SF divided by SFG, and SFG is just the difference between SG and SF. So that would be 7.3870 minus 1.0912 divided by 6.5019, which would be 96.83% of the mass, the total mass, is in vapor phase. Now I know that in my table, let me write it. Yeah, it's worth it to write it there. I know that x2 is what was that? 96.83, which means if there's a mixture. But on the left side at point 1, we had a superheated steam. Great. So what am I looking for? I'm looking for, tell me. I'm looking for H2. See, I told you here that now H2S has changed. And I have the mixture, and the quality, and I have the pressure and pressure. So please pay attention that when you are assuming that the process was happened isentropically, then the temperature would change, right? Because there's no loss, there's no friction, but the pressure is the same. So here that I defined isentropic efficiency for turbine and compressor, we assume that the compression ratio is the same. That's why I did not change this pressure. I found everything at the same outlet pressure at the outlet. But the temperature definitely changes because now the process is isentropic and we're going to have less friction, like no friction, or all these intermolecular reactions and like interactions. Therefore, temperature would be lower, right? Anyway, just keep in mind that the compression ratio is the same. Don't touch the pressures. And I was looking for enthalpy as if it was isentropic. The process was isentropic, and I know that I can solve for enthalpy this way. At 50 kPa, the pressure is still same as what it was at the outlet, 50 kPa. And if you go, let's go to the table. What's the table? A5, I guess. Yeah, it should be A5. So here, 50, right here, A5. Yep. We're looking for enthalpy. Uh-oh. That's it. Here's HFG, and here is HF, 340. Well, okay. We're about to finish this solution. So now I am ready to go. Therefore, W dot S means isentropic outlet equals M dot times H1 minus H2. Oh no, 2S. 2S. You need to keep this in mind. 2S. Now everything is isentropic. I'm looking for this guy. Plus, and velocities are the same. Velocities are the same. Just the enthalpy has changed. Only the enthalpy. The only effect, the only influence of this assumption, isentropic, kind of like assuming ideal turbine, it just changes the enthalpy. Only the enthalpy. Just the enthalpy. Everything is the same. Therefore, equals and H1 is still the same. It's just the inlet of the turbine. It's not gonna change according to like assuming it was isentropic. Because when we assume that the process was isentropic, it means from the inlet and then whatever that happens in the turbine, then in the outlet. So the effect would be on the outlet, not on the inlet. Inlet is the same. And likewise in compressor. Minus. So that's a change in enthalpies plus same for velocities. Just put in the velocities. And once I forgot to write, but the units here is like kilojoule per kilogram. Yes, but here it is in meters square divided by second square, and I need to convert that this way. Yeah, you need to know this conversion. You need it. And that would be 9670. 3.5 kilowatt. Perfect. Now the enthalpy, perfecto. Now the enthalpy, oh, sorry, the efficiency, the isentropic efficiency of turbine equals W. Tell me, think again. Let's think about that ideological world. In an ideal world, think you can pause and think and then play me back again. So in an ideal world, a good turbine, an ideal turbine, uh, possessing same compression ratio, I mean like pressure ratio at the inlet and outlet, at the same identical pressure ratio, a better turbine gives us less work or more work. More work, definitely. And the actual work in the real world, real nature, would be less. And I'm defining a portion that it's going to be less than 1. So the one that is less, that is smaller, should be in numerator. And the larger one should be in the denominator. So the smaller one was real world, actual world. So the actual work at the outlet divided by the isentropic. In a good world, in the ideal world, a good turbine gives us more energy. See, I'll show you. I'll show you. Yeah, isentropic. Oh, S. Yeah, outlet. This guy, we found it as 9673.5 kilowatt, and the actual work is 8,000. See, it's less. It's smaller. In the real world, the actual world is 8,000, but in an ideal good world, the power, the output power is larger. Therefore, the isentropic efficiency of turbine would be 82.7%. Thank you so much for listening to this lecture. I hope that I taught you something and you learned something. Um, that's it about the isentropic efficiency for a turbine and all sort of things that we have learned. Thanks and bye.